16.45 is a little better. But same thing goes for the population variance. That just means you're going to take the population standard deviation and square this number instead of squaring the sample standard deviation. Again, you only know that by is if the description implies a sample or if it's implying a population. And you can calculate the variance just by squaring the standard deviation, either of the sample or the population. But what are these good for? So here's just some notations. So again, S is sample standard deviation. S squared is the sample variance. Lowercase sigma is the population standard deviation. Lowercase sigma squared is the population variance. So just all you have to do is square the standard deviations and I'll give you your variance. Again, we haven't really seen an example with the range. We got to see how you do a quick calculation and it gives you an idea of how spread apart your data values are. Even though the standard deviation tells us how our values deviate from the mean, we haven't actually seen an example of how that works. And the way it works, it uses this idea of the empirical rule. So the empirical rule for a data set that's bell-shaped distribution. And not just any bell shape, it wants to be roughly symmetric. You want to make sure you have a rough bell-shaped symmetric curve. That I think we talked about right before all this started. We saw the different distributions. There's a skewed left, skewed right, and then there's the symmetric, there's the uniform, and then you have your uniform is symmetric, and then you have your bell-shaped symmetric. Because skew left and skew right are roughly look bell-shaped, but they're not symmetric at all. So this empirical rule, we're going to see a picture of it right now. And what this picture tells us is how our data values are deviating away from the mean. So, and this is how it breaks down. The empirical rule states that for data sets having a distribution that's approximately bell-shaped, the following properties apply. So about 68% of all your data values fall within one standard deviation of the mean. Again, one standard deviation is so one standard deviation in this example that we're looking at, 16.45 is one standard deviation. Two standard deviations would be just adding another 16.45 to that 16.45. If you can get three standard deviations, you have to add another 16.45. So that's what it's when you say one standard deviation, it's not about this one value, which is 16.45. That's one standard deviation. Two of them would be adding those two of these together. Three of them is adding three of them together. And that's what this is saying here. 68% of your data values fall within one standard deviation of the mean. About 95% of all your values fall within two standard deviations of the mean. And about 99.7% of all your values fall within three standard deviations of the mean. And here's a picture of how that looks. And here's the empirical rule. Let me see if I can zoom in a little bit. Hopefully this helps. There we go. That's a little nicer. And I'm going to show you another empirical rule. This one, some of the numbers are not that they're off, but they're more accurate. So we already got to see how our calculator is, if you did it by hand, you'd have to be rounding things off, which might not be the most accurate. Or our calculator is very accurate. Sorry, I'm trying to zoom out a little bit. this. Okay, so that, if you look at down here, this is 1 standard deviation. You're going 1 standard deviation above and 1 standard deviation below. Again, this doesn't mean the standard deviation is negative. You're just subtracting 1 standard deviation and you're adding 1 standard deviation. Once you do that, you get approximately 68%. And this is what I'm saying about being bell-shaped and symmetric. That means if I cut this down the middle and I fold this, everything should line up nicely. And you can see that if I fold perfectly here in the middle of that, everything will match up. So it's bell-shaped and it's symmetric. So if you go 1 standard deviation above, 1 standard deviation below, that creates a window. The same way the range created a window. But the range, the window the range created was taking the biggest and the smallest and giving a rough idea of how wide your data values are, how spread apart they are. And this is how the standard deviation does that. In the empirical rule, is that if 1 standard deviation below, 1 standard deviation above, there's 68% of data values should lie within here. But if you notice, 34.13 plus 34.13 does not give you 68. So if you try to use your calculator would give you a little bit more than 68%. That's why it has that 0.13, and then there's these 13.59s and all these little extra decimal values. So I'm going to show you another one that doesn't have, it just has 34 and 34. And you're going to see it's going to be a little slightly different, but it matches up with these 68, 95, and 99.7%. What these numbers are doing are being a lot more accurate than these are being, but it's roughly the same. Again, it's not a huge difference. It's just 0.13 of a difference. But let me continue. So this is, when it says 1 standard deviation, it's implying that you're going above and below. If you're only going 1 standard deviation above, it would strictly say 1 standard deviation above or 1 standard deviation below. If all you say is your 1 standard deviation and you don't say above or below, you assume it's both. So now, if we look back, if we say about 95% of our data values fall within 2 standard deviations of the mean. So again, it doesn't say above or below, so you assume it's both. So we go 1 standard deviation, 2 standard deviations. And within 2 standard deviations, all this in here represents 95% of your data values. And now when you go 1, 2, 3 standard deviations, that means all this in here should represent 99.7% of your data values. As you can see, the majority of your values are already within just 2 standard deviations. That's where the majority of your data values lie. And that's the nice thing about this, the standard deviation. It gives you a better idea of where your data values are. So as long as you know your data set is bell-shaped and symmetric, within 2 standard deviations, even within 3 standard deviations, that's where majority of your data values should be. Where the range doesn't really give you a good, if you use it for this data set, it doesn't give you a good idea where the majority of your data values should be. Where the standard deviation will take every data value into account. So we'll see that right now. But let me show you this other empirical rule. I mean, it's not another empirical rule, it's the same thing. But with this one, you can see, let's see if it lets me zoom in. Oh, perfect. This one, you can see that is just saying 34. So within 1 standard deviation, it doesn't show the mean, or there's the mean right there. So if you're 1 standard deviation from the mean, again, that implies both above and below. This represents 68%, which it makes sense. If you do the half of 68, that's 34. And then 2 standard deviations, so that's 1, 2, 1, 2. Now that ends up being 95%. So that's what makes up these leftovers. That's why these are exactly the same. And then 3 standard deviations, then that means these last little bits are 2.35, 2.35. And you can see how that's slightly different than this one, because it has that 0.13. So if you add this 0.13, then it's changing this one a little bit and changing these a little bit and giving you even just a little bit more. I'm okay with this. If you're able to find this online, I'm okay with you using these numbers. I don't care so much about you putting 34.13. I'm good with 34, 13.5, and 2.35. That's enough for me. And then here are these numbers up here. It's saying 50-50. And the reason why it's saying that is just, again, it emphasizing the idea of being symmetric. If this is bell shape and symmetric, that means symmetric. If you fold this in half, everything should line up. That means on this right-hand side, that's where 50% of your data value should be. And on the left-hand side of the mean, there should be another 50%. So that's just something to keep in mind, that it's symmetric. So that means this represents 50%, this represents 50%. But then if you're just talking about one standard deviation, this is 34, this is 34. If you're talking about 2 standard deviations, the extra, you add on 13.5 to 34, you add 13.5 to this 34, and so on and so forth. So don't still know these numbers. So these 68, 95, 99.7. That's the same thing this one is saying, 68, 95, 95.7. What's deviating here is just these little decimal numbers that they're adding on to it. So don't let that confuse you. Hopefully it doesn't. But this is how the empirical rule works. It's using the standard deviation to give you an idea of where your data values are. Imagine this is a number line. So remember, number lines go from least to greatest, and there's the mean in the middle. Your data values, if you actually were to plot them on here, they are somewhere within all these numbers. And it just happens to be, as long as it's bell-shaped and symmetric, you have these different percentages of your data values that are within those standard deviations. So look at a quick example. Oh, sorry, I'm moving the whole thing. So again, if we're using the empirical rule, it says IQ scores have a bell-shaped distribution with a mean. So IQ scores happen to be bell-shaped. By bell-shaped, we're also saying, implying it's symmetric, with a mean of 100 and a standard deviation of 15. So when you say 1 standard deviation, that means 15. And the mean, so if we go back to here, this would be your 100, and S is your standard deviation. So you can add 1 standard deviation above, or 2 of them, or 3 of them, or you can subtract by a standard deviation, or by 2 of them, or by 3 of them. So if we look at this example, we can try to construct a empirical rule, but using these values. Here is just using symbols. We can actually create an empirical rule, a bell-shaped curve, using the fact that we know the mean is 100, so that's going to be the middle, and our standard deviation is 15. And then we have to try to answer these questions. What percent of IQ scores are between 70 and 130? What percentage of IQ scores are within 3 standard deviations of the mean? And what percent of IQ scores are above 130? So to get that, we have to try to construct the empirical rule. So let's see if we can do that together. All right, so I drew this box to help me see what my camera is doing. So, and we're going to do, we can think about this as our number line, and then we have our bell-shaped curve. And I try to make it as bell-shaped and symmetric as I could. Don't forget, if this is symmetric, that means the middle is where your mean is. And we know what the mean is. This said that the mean of IQ scores is 100. And we know the standard deviation is 15. So if I'm going to do one standard deviation, that means I need to add one standard deviation above and subtract one standard deviation below. So I'm not sure if I pressed record while I drew this entire graph. So I'm going to explain it again really quick. I think I pressed record, but I'm not sure if I did. So again, this is a bell-shaped curve that's symmetric, meaning that if you fold it in half, both sides would equal to each other. And the example said that we're looking at IQ scores are, the mean of IQ scores are 100 and their standard deviation is 15. So if I want to do one standard deviation, that means I'm adding 15. So 100 plus 15 gives me 115. And then I subtract 115, which gives me 85. And that gives me one standard deviation. So 68% of our data values are within one standard deviation. And then I add another 15, that gives me 130. And then I subtract another 15, that gives me 70. Now within here, all of this represents 95% of my data values. Now if I go add 15 one more time to that, I get 145 here, and I'm going to subtract 15 one more time. And that's 3 standard deviations. Again, if you just say 3 above, they're just adding 15 3 times. If you say 3 standard deviations and you don't say above or below, you just imply it's both. So you're adding 15 3 times and you're subtracting 15 3 times. And that in here, if you add up all these percentages, that'll add up to 99.7% of your data values are within 3 standard deviations. And this is how you would set up your bell-shaped curve. And now we want to answer some questions. So this first question says, what percent of your data what percent of IQ scores are between 70 and 130? So if I look here, here's 70 and here's 130. And I know that's technically 1, 2, and 1, 2 standard deviations from the mean. And that's 2 above and 2 below. So that's strictly 2 standard deviations. And we know that 95% of our data values are within 2 standard deviations of our mean. That would be our answer for number 1. Where the next question was, what percent of IQ scores are within 3 standard deviations of the mean? This was slightly a trick question because you don't need to draw the graph to see 3 standard deviations. That's just the rule. The rule says if you're within 3 standard deviations of the mean, again, it's not saying above, it's not saying below. So that it means it implies both. So that means 3 above and 3 below, which for all bell-shaped symmetric curves, 99.7% of your data values are within 3 standard deviations. Now the last question says, what percent of IQ scores are above 130? So that means I'm strictly only looking at everything above 130. So that's everything on this side. The nice thing is that all of this is symmetric. So if I'm looking above 130, well, like how I said a second ago, since this is symmetric, I already know all of this represents 50%. And I know this is 34%. So these two together, now I'm at 84%. Now I just need to add this extra little portion. Again, I'm at 84%, so let me move up. I'm at 84% so far with the 50 on this left hand side plus this 34, and now I'm just gonna add. And the reason why I'm adding is because I know this entire curve is 100%. If I add these extra little pieces beyond 3 standard deviations, this whole thing is 100%, because that just means the whole and all your data values are on this number line somewhere. So 100% of them are in here somewhere. The question was looking for strictly above 130. So that's not just this little piece here. It's even the extra little piece that we didn't actually draw. So it's not just this, it's also including this extra piece. So that just means if I can take this off, then whatever is left over will be this portion. And again, if I add 13.5, that ends up giving me 97.5. And then that's just adding from 130, everything to the left is 95%. Whatever's left over is the percent of IQ scores above 130. So all I have to do here is subtract that from 100, and that ends up giving me exactly what's above 130, which is going to be 2.5%. That would be our answer. So again, that were these 3 questions. We had what percent of IQ scores are between 70 and 130. Again, here was 70, 130. That's 2 standard deviations above and below the mean. That represents 95%. In the next question, we already know what percent of values are within 3 standard deviations. As long as we know it's bell-shaped and symmetric, it has to be 95%. Sorry, 99.7%. And then what percent of IQ scores above 130? Well, all we're looking at is whatever's left over. We know there was a 2.35. What was left over here is 0.15. Adding those together will give you 0.25. Or you can try to add all these here, which you know this represents 50%. This here will give you your 47.5%, which is a total of 97.5. This whole thing represents 100%. So if I just take this portion away, I'd be left over with what I'm looking for, which is above 130, which ends up giving you 2.5%. Which here were their solutions. Again, the key is to recognize that 70 and 130 are exactly 2 standard deviations away from the mean of 100. 2 standard deviations is 2, which would be 30 above and 30 below. So hence, that's 95% of all IQ scores are between 70 and 130. And then I went over the other ones so you can see what they are. And again, how you get your standard deviation from a data set? You just input your data. Let me turn this on. You input your data into your table. So remember, stat. Hit enter. Input your data here. Then you go to stat. Go to calc. Then enter on one var. Whoops. So if you did something wrong, hit second. Quit. And let me try that again. Oh, I'm hitting plus. I have to hit enter. Then once you get here, so let's do it again. So remember, if you're going to input your data values in your table, you hit 1 or enter. Just remember where you put your data values. Then you're going to hit stat. Go to the right under calc. Either press 1 or enter. And then it doesn't matter which you're looking for, but make sure it does matter. Make sure you put the correct column, and then once you calculate, you'll have your standard deviation. Again, there's the sample and there's the population. Depending on what the example is telling you about, or what the description is, you have to be able to determine if it's sample or a population. And that tells you, again, the larger the standard deviation, the farther apart your data values are. The smaller it is, the closer. If your standard deviation is 0, that means everything is exactly the same, which we saw that earlier in the video. But this rule only works for this bell-shaped symmetric curve. But we did talk about skewed left. We talked about skewed right. So whenever that happens, let's say when you don't know what the distribution is, again, if you know it's bell-shaped and symmetric, that's great. You can use the empirical rule. But what you don't know, that's where this idea of Chebyshev's theorem comes in. This is strictly for if you do not know your distribution. If you know it's bell-shaped, then go ahead and use the empirical rule. But if you don't, here's this theorem that tells us, again, it's trying to do the same thing. One standard deviation for the empirical rule is 68% are within. So 68% are within one standard deviation, 95 are within 2, and then 99.7 are within 3. What the Chebyshev's theorem says is that depending your K standard deviation, so by K like 2, is it 2 standard deviations or 3? K is just some arbitrary number. And when you're within some number of standard deviations, that means the percent of data values are within that many standard deviations is at least 1 minus 1 over K squared. So here, when you are at 2 standard deviations from the mean, that's about 95% of your data values are within 2 standard deviations of the mean. If you're using the empirical rule, let's say we have 2 standard deviations. So for the empirical rule, it was 95%. For Chebyshev's theorem, when you're at 2 standard deviations, when you plug in 2 here, that simplifies to 3 over 4. So for the Chebyshev's theorem, it's at least 75% of all values lie within 2 standard deviations. Here, about 95 of all values are within 2 standard deviations of the mean. This is at least 75 of all values lie within 2 standard deviations. Here is at least 89% of values lie within 3 standard deviations. For the empirical rule, it's 99.7 for 3 standard deviations. For Chebyshev's theorem, it's at least 89%. Or at least 75%. So if we're doing a similar example, let's say we did not know if the distribution was bell-shaped. But we did know that our mean was 100 and our standard deviation was 15 still. What can you conclude from Chebyshev's theorem? Depending what example you're doing, let's say if we're trying to answer this, what percent of IQ scores are between 70 and 130? We know that between 70 and 130 means 2 standard deviations. If they're not bell-shaped, then you would have said at least 75%. If you're using Chebyshev's theorem, what am I doing? If you're using Chebyshev's theorem to answer this question, what percent of IQ scores are between 70 and 130 IQ scores? Between 70 and 130, that represented 1, 2, 1, 2, 2 standard deviations from the mean. So that means at least 75% of IQ scores are within 2 standard deviations of the mean, between 70 and 130. If we did 3 standard deviations from the mean, that means at least 89% of IQ scores are within 3 standard deviations. 3 standard deviations is 1, 2, 3 above, 1, 2, 3 below. So that'll be between 55 and 145. That's exactly what it says here, between 55 and 145. It's at least 89. At least means that's the bottom. It could possibly be more. If it's bell-shaped and symmetric, 99.7 lie within 3 standard deviations. And that's it for that. Again, this ideas from last time we talked about how can we measure or calculate the most common data value. That was either mean, median, or mode. This was helping us to see how spread apart, or the spread of our data values, the variation of them, so how they spread. The range just gave you a window of how far apart your data values can be, but it's not resistant because very large or very small numbers can affect it. The standard deviation takes every data value into account to give you an idea where your data values are. And as long as it's bell-shaped and symmetric, you can use the empirical rule to give you an idea of where your data values lie relative to the mean. Let me give you some homework. Hopefully you can try this a little later. Here's your homework. Like I said, right at the end of the video, for 3.2, 5, 6, 7, 11, 12, 41, 42, 43, 44. So it's only a few examples. If you have any questions, please email me or show up to my office hours through Zoom, or you can send me an email if you want to schedule a one-on-one Zoom time. That works for me too. Just email me and then we can set that up. Thank you. Bye.